Hi, and welcome to this week's webinar on utilizing the Decision Center in Autodesk CFD. My name's Matt Bemis, and I've been supporting CFD here for a bit over a year. I'm based in Boston, Massachusetts, but support people pretty much all over the globe. Today, I have with me David, so go ahead and introduce yourself.
Yeah, hello. As Matt says, my name's David, and I'm part of the technical support team based in Munich, which means that I work with the European and Middle East cases. And yeah, so thank you all for joining, and I look forward to hopefully supporting you with your projects in the future. So back to Matt, and then I'll go through an example at the end.
Awesome. All right, so contents of today's discussion. We're basically just going over using the Decision Center, which is a post-processing feature that really lets you speed up your, overall workflow and time and just get answers faster. So when you're using the product, usually you have one question in mind or one, something you got to figure out. Some kind of design criteria, and this really helps you extract results in a really fast way and have some luck there. All right, so we're going to go through a few demos. I have a pretty cool electronics box model. It's an Nvidia board where we're varying supply air temperature, and David's going to go through a pressure drop through the valve. Now again here, you're going to be stepping through different scenarios where you change material settings or change boundary conditions, and you can post-process extremely fast, get the answer the questions you have very quickly. All right, so just to cap off some kind of clarify some information here. In CFD, we have the design study bar, and it has different scenarios and different designs. So a different design means you have different geometry in different CAD. That's the main differentiation there. And then within there, you'll have different scenarios. In the different scenarios, you can have different mesh settings, different solver settings, material assignments, boundary conditions, really anything else. But between two scenarios, your CAD's the same, and so I just wanted to clarify that before we kind of dive into the rest of this webinar. So what is the Decision Center? Like I said, it's really a way to extract results extremely fast and just get answers to the questions you have. So instead of going into every design scenario, which you could have 10 or more at times, you just have to go through a workflow once, like you add a summary, add a plane, add some points for an XY plot, and then you just hit make summary, and the workflow will be done for all your scenarios and if possible, all your designs. So it just takes the mundane, boring, and tedious work out of post-processing for you. And all you have, then you go into the design study, or the Decision Center, right click, say update, and boom, you got the answers you need there. So and everybody who uses this tool is always varying things. I mean, there's so many parameters here that can almost be daunting at times to understand what your what is affecting your results. Is it a turbulence model, or is it mesh, or an advection scheme, or both? A lot of folks are still uncomfortable with understanding and obtaining a good mesh, and this really helps. You can look at your critical values, your design criteria, and change the mesh and figure out, are my results changing or not? So for my example, I have a Nvidia Jetson board. I grabbed this off of GrabCAD actually, and yeah, so basically I use this for an electronics webinar earlier on. As a design criteria, if you're an engineer designing a cooling system for this, you might want to understand what's your maximum, inlet ambient temperature, which will allow the boards allow the chips to still operate in an acceptable range. I have a little experience here in the data center business, so I know, rack inlets on servers have to be under 27C, or that's the ASHRAE spec there. And nowadays, just oversizing fans or just kind of over engineering it is kind of wasteful and stupid. So, um, you might want to understand what kind of environment can a board like this operate in, and when do things really go south. All right, this is just a quick graphic. I'm sure most people know, but um, the average lifetime of a chip really drops off with respect to temperature of the chip or the junction temperature. So, and this is something that's studied with a lot of, vastly, and is really a big problem. If your chips run too hot, they will burn up very premature in their expected lifetime. And so this is always in the mind of a electronics packaging engineer, and they're always focused on where are the chip temperatures and under what conditions. So here's my Nvidia basically board inside of CFD. So on the left, I have a aluminum box around it. I have an inlet and outlet, exhaust. I built this stuff. This isn't like from the manufacturer, but I have that internal fan right there, and just an extended inlet and outlet. So basically, air comes in the top. It hits one of the top chip, highest heat load chips, and exhausts over on the right side there. Hiding the aluminum box, I basically pointed to the chip I want to, I really care about. So in your design, this is the highest heat load, or it's the farthest away from air. In my model, it's kind of in the back corner, and you want to, understand what's that chip temperature like at different supply temperatures, different ambient temperatures. All right, so in order to create a summary part, all you have to do is grab the, when you're looking at the results tab, click parts calculator, and then select the chip and check that box, which will make it a summary part. So what this means is you only have to do this once in all your different scenarios. And by the way, there could be a ton of them. And at that point, you can just go to the decision center, hit update, and now you understand the chip temperature for all your different scenarios. So again, you could vary supply temperature, flow rate of the fan, etc. Again, so from the results, the next one over, this is this workflow is built on purpose, left to right. Go to the decision center. Over on the left there, you'll notice that you see an exclamation point, kind of like a warning under your summary values. This means that what's sitting in the decision center is outdated. So you could have changed the location of a cut plane or change boundary conditions or something. It just means, and this is very important, it just means you need to update what is in the decision center. So it only really pulls information from the scenarios and designs when you tell it to. So here, all you have to do is right click on any of those exclamation points. It's top to bottom, and just say update summary part. So, I went through that workflow, and here's my 4 different designs. So I have supply temperature stepping up, starting with 25C, stepping up 5 degrees C all the way up to 40. and you can look at average, maximum, and minimum temperature, which is exactly what we have while in the results dialog box. But again, you don't have to create your own Excel sheet on the side or start scribbling things down on a notepad piece of paper. So here, we understand, at 25C, your average temperature is probably acceptable. 30 for most commercial applications, it's pushing it, and after that, it's too hot. So, 88C is pretty warm for a chip, and 90, 94, 100 is too hot. All right, so what I'm going to do is hand this over to David, and we can loop back and kind of jump into CFD in a moment. I'll have David share what he wants to share, and then when he's ready, we can bring it back to me, and I'll show you my model inside of CFD here. So just give me a moment here.
Hey everyone, this is Marwan. In the meantime, I just wanted to make a kind of a high-level comment here that, you might be wondering what goes into the decision center. Well, you can put anything that you want in the decision center. You decide, is it going to be a cut plane? Is it going to be a part summary? Is it going to be whatever it is, a plot, XY plot? You decide what goes into the summary there in the decision center. What's important to you to make the comparison?
Yep, exactly.
Okay, thanks Marwan, thanks Matt. So I'm going to run through quickly a mesh study. The decision center can be super helpful for this in visualizing the difference between meshes and comparing the effect of these meshes on the flow. So we're going to look at 3 different meshes, which means we're going to look at 3 different scenarios. One in which the model has only been meshed using automatic sizing and no manual refinement. One with automatic sizing plus I've done some manual refinement following meshing good practices, well, hopefully. And then we're also going to apply mesh adaptation. And I'll talk about that as well. So the mesh adaptation we're going to use to develop the final mesh for analysis. So mesh adaptation, it's an iterative process that it'll run the initial scenario to convergence, and then it'll progressively improve the mesh based on the previous scenario. So where there are really high flow gradients in the velocity, the pressure, the temperature, it'll refine the mesh because we need tighter refinement to accurately define the characteristics of the flow. There's also an option to coarsen the mesh where there's low gradients, and this can save you element count and reduce your runtime. So to enable this, we enable it in the solve dialog, and I'll show you how to do this in the CFD user interface in a minute. But then you define the number of adaptation cycles, and you check save, and we check save that so we can visualize each cycle. Yep, and yep, always it is better to apply meshing best practices before you apply the adaptation rather than just going with the automated mesh, because it's an automated process and you're probably better with a bit of manual refinement in the areas of interest.
David, I'll just add, sorry about that. I'll just add one point too. I, as a end user that, uses it every day, I really enjoy saving the intermediate, cycles. Sometimes my last and third or second and third cycle will really marginally improve the results or the mesh independence. But the element count goes way up and the solve time gets way longer. And so if you tell it to run 3 cycles, it's going to run 3 cycles, but the intermediate one may be completely sufficient. So I like the save one. It's just a personal preference. And sometimes I go with that intermediate one.
Yeah, absolutely. And I've actually only run 1 cycle because I got pretty good convergence out of that. And also the next cycle, I tried to run it, and the time it took was getting pretty ridiculous. So But what we can do with mesh adaptation is it can help to identify a mesh independent solution. So one in which the solution doesn't vary if you refine the mesh further. And this is obviously what we aim for in CFD. And what's nice is when we're running mesh adaptation, it gives us an indication of this in the output bar. So where you see these percentages, that is a percentage compared to the values of the previous simulation. So 100% being absolute convergence. So we'll show, and I was in the 90s on the first adaptation cycle, so pretty happy with that. What we're going to do, just running through what we're going to do before we go into CFD, is we're going to compare the mesh refinement and the flow details using summary images. And then we're going to use planes to look at the pressure drop over the whole system, the total pressure drop. And we're also going to use a summary XY plot to look at the pressure drop, a detailed pressure drop over the valve. So, and here is the model we're going to look at. And I've nicked it off GrabCAD. So I want to give some credit to Sohail Khan. So thanks a lot for sharing it on GrabCAD. Really nice model. So we're going to pop over to CFD now. Okay, let me try and get rid of. Okay, so as you can see on the left in the design study bar over here, we've got the scenarios as we defined earlier, the auto-sized, so just using automatic mesh, and then manually refined mesh, and then refined M2 is the mesh after one cycle of adaptation. So if we step into this scenario, and you can see what we've done here is with the CAD model in Inventor, split it down the middle because it's symmetrical on both sides, and then this will half the element count, obviously, and that's really good for reducing runtime. And then you have to create an extra part here, just so that the internal fluid volume within the valve that we've got here is actually is contained. So then CFD will automatically make a solution domain in the volume, and that comes in here as volume 13. So if I hide these guys and okay, so if we look at it from this angle, deselect where we get a bit of a clear understanding of what's going on. I'll just hide this central volume as well, and then we can really see what's going on. So here's the valve, the water comes through here, and here are the openings that go all the way around. Okay, so here's the inlet and here's the outlet. And what we did with meshing was I refined this internal volume. Hang on. Here we go. So I refined this internal volume here with a bit of manual refinement, and also along this edge here. So you can select this, go to surface here, select that edge, edit it, and then if you bring this down, you could control the level of refinement here. And I assumed that we're going to have some complex flow being initiated here, so I wanted to get a bit of refinement there. Also in CAD, extended the outlet and inlet. Could have actually gone a bit bigger here because it's good practice to have 5 times the length of the diameter of the inlet and outlet to help your simulation avoid recirculation at the outlet. Okay, so and then once we meshed it, then went to solve, turned on adaptation here, as you can see, running cycles, and that is what created the next scenario, Refinement M2. And we'll go to the results of scenario 1, Refinement M1 to start off with, because we're going to start making summary images. And this is obviously the global view, and we're looking at the outside or the surfaces of the volumes. So the outside surfaces of the volumes. And I'll change this view to shaded area, so then we can get a nice view of the mesh on the outside surface, on the symmetry plane. And all you do is, when you're in results, to make a summary image, go to here in the top left, summary image. And once that's been made, you go over to the decision center. You update the image. Hang on a minute. Bear with me.
Add some patience.
Yeah, here we are. Okay, so now we're in the decision center. And what is definitely good to do is change the viewport, so then you can see all your scenarios up here. So then if we hide the output bar, as you can see at the moment, it's all the same scenario. So if we go here and remove frame. So this was our automatic mesh. And here is our Refinement M1 and Refinement M2. And so we can see what's happened here. So with the manual refinement, we've got a bit nicer or a bit better detailed mesh around the openings to the valve, and even further with the mesh adaptation. So you can see how many extra elements were inputted with that one cycle. And as I said, with that one cycle, we had nice convergence. So, and then here is a couple of other images that I created earlier to have a look at the flow. So then you can see that we're definitely getting more flow detail being defined with M1, M2. With our M2 here, we've got much better definition of the flow coming through the valve. So that's shown nice results.
Yeah, your velocity is more jetted, basically. Again,
yeah, good point.
This workflow just really helps you, whoever you're presenting this to, whether it's a manager or a company you're doing consulting for, you can build up faith in the results by demonstrating. My results are mesh independent, and look at the difference between the different meshes as I increase. It's really easy to see. You'll see gradients. You'll see more mesh around gradients, high gradients, and you won't be able to see elements or nodes, basically, with the mesh turned off. So the decision.
So let me just show that as well. I can show that with putting a plane in. If I put a plane in here in the results ribbon. If we line that up with where we want it, so now we're actually inside the volumes, and we can, if we come here, that's where the detail is, or where the flow is the highest on that plane. If you make a summary image of that, go to the decision center, update.
And using the cut point is really nice because you're not looking at that slip symmetry face in the global results. You're actually down inside as if you're cutting it, right down the middle or so.
So if we look at the auto-sized mesh, you can almost make out the mesh here.
Exactly.
And that's what Matt was talking about. So we know that isn't physical. I mean, there is no mesh in reality, so we shouldn't be able to see or visualize the mesh in the results. So it's too high gradients. Whereas if you look in Refinement M2, that's a bit smoother. Still not perfect, but smoother. So we can say that is better.
Yeah, a lot better. Looks a lot. I think it looks great.
Okay, so now next we're going to look at, if I get rid of this plane, we're going to look at a summary plane to calculate the total pressure drop over the entire system. And if you see my boundary conditions here, I've applied a pressure 0 on the outlet. And this means that at the inlet, if we measure the pressure at the inlet, that value is actually going to give us the pressure drop over the entire system. I hope that made sense. So if we add a plane, and if you select align to surface, rotate it round so we can see the inlet and chuck it on the inlet. And then if you go up to the top right and you say make summary, so we're making this a summary plane now, and head to decision center, you've got to always update your summary values, planes, points, whatever. Update the summary values. And so here's our tabulated results. And if we select the pressure row here and say plot selected rows on the right there, then we can see the total pressure drop through the system for each different mesh. So obviously M1 and M2, there is a difference, but the difference is significantly smaller than the difference between the refined meshes and the auto size. So that's another indication that we've got fairly mesh independent results. Not perfect, we could have done a few more mesh adaptation cycles, but this gives an indication of it anyway. Okay, Matt, anything to add on that? Because
Sure. So a lot of times I do use planes right through the inlet and outlet, kind of like David just did, and I will name them inlet and outlet. So I've spent a lot of time helping customers get pump models right, where we're trying to get the pressure delta across the pump right. And this just lets you, you're going to end up trying a bunch of different things, and this just lets you, you only have to assign the inlet and outlet plane once, and then it's there. You can run as many scenarios as you want, and you can just update the summary value and figure out your pressure delta. It lets you eliminate, bad approaches quickly and keep the good ones.
Yeah, nice. So we're done with summary planes now, and the final thing that I'm going to run through is a summary XY plot. And you do the XY plot, you do it on a plane. So let me just get rid of this plane. Yeah, go on then. Okay, so now if we align it nicely, and I want to do an XY plot through the valve opening to get a detailed pressure drop, and then align it again. And if we bring that, ooh, oh, I hate this. Right, I'll just remove that and start again. So we've got a plane in a nice area where lots of complex flow is going on. And then on this plane, we can go top right again and XY plot. Add by picking, you add points, and then we're going to plot at each point and interpolate between it. So zoom in here, and then you can select your points to go where you want to plot your data. And we're going to go take it through the valve opening. And then all the way down to where it's sort of settled a bit. Okay, and then you can press plot here. And we're in velocity at the moment, so it'd be interesting. What we're looking at is pressure drop. So change this to static pressure, and then we can see the pressure drop through the valve. And if you tap summary here, it's going to make it a summary XY plot. And you can close that and head over to the decision center once again. And there's our plot. So you update the values. And here it is.
Awesome.
So now we've got a plot of the 3 different meshes of the pressure drop detailed through the valve. And that's a really awesome thing that the decision center can do, because that would take so much time to do on Excel or something, you know. And that's a really great feature. So I think that's all I'm going to go through. I'm going to hand back to Matt, because he's got a couple of, or he's got a technical support story regarding something similar.
Sure.
So let me just change the presenter. To
I think I got
interesting.
it, David.
You got it?
Yeah.
Okay, great.
All right. I think you can see my slide, David. Can you confirm?
Yeah, I've got it.
All right.
Looks good.
So I just wanted to share this support story. Obviously, I use CFD 40 hours a week, every week, and utilize the decision center all the time. The way I'm doing support, I've got to scrap bad approaches fast and stick with good ones and move forward there. So a while back, I was trying to help a customer get the expected pressure drop across this valve here and model it correctly. And so it ended up being a big, pretty serious problem. I mean, we've got to match experimental data within a certain percent, or else customers aren't happy. And there's a lot of parameters to vary. So, the customer asked me, do you think it's mesh or do you think it's, turbulence models or, advection schemes? Is my convergence criteria tight enough? Those are all parameters. And when you start, when each can influence the other, you start to get so many scenarios that it gets pretty daunting. So this was a model where I basically used an XY plot, or I used both an XY plot, and I just used my approach of having an inlet and outlet summary plane, and just kept trying things and incrementally improving my pressure drop. So here, and again, the decision center kind of gives you a nice sanity check here, because you want all your planes to be in the exact same location. You don't want them to be off by a few centimeters left or upstream or downstream. That can really make a big result, and you don't want to make mistakes with units or really anything else like that. So these are all driven off the exact same plane, and that the location of the plane hasn't been moved, or else you're going to get that warning there in the design study bar. So again, here I tried I think 8, and at one point there were more than 8. And again, you can see my planes. They're upstream. I named them upstream, downstream, and we started crunching the numbers to look at pressure drop in bar, and finally got a very good result. Less than 10% in a symmetry model, which is not too shabby. And so, we were able to, I was able to give this to the end user and a reseller, and they were pretty happy. So, we all know even switching between scenarios takes a few moments, and the more clicks you have to do, the more prone you are to user error, basically. And I'm obviously guilty of it too. It happens all the time. So I really like this workflow, and it definitely gives me peace of mind. And there I plotted, with my XY plot, the different approaches. Pretty interesting, you know, not to go on a side story, but some of the approaches were definitely proven bad, you know, and were insufficient. And so I was able to, you know, figure out what worked, and then taught the end user to take this approach as a best practice. And by the way, this is, if you have doubt, this is how you can check. Customers ask me all the time, you know, how much of my results going to change if I run till tight convergence? And I really, you know, have no idea, because every project is really different. So what you can do here is just clone a scenario where it converged. You can clone it with the mesh and with the results. Set that convergence to tight, or turn off, you know, auto convergence detection, and just run it and look at how much your results look. And you can do that very quickly. You know, we pick default, so it hopefully doesn't change too much, but every engineering simulation is different than the next. So yeah, so at this point, I'm just curious if anybody has any questions, you know, flaws in the workflow, or hiccups, or you know, user issues. Just like every webinar, you can just ask questions in the dialog box that you have, and send them over, and we'll try to answer all of them here. So we'll just give it a few minutes. Again, please feel free to ask any questions you have, or any comments. We can discuss it. If you have a specific design problem you're trying to solve, and you're saying, you know, what results should I just extract, or you think there's results that can't be extracted correctly in the decision center, or, you know, I'm happy to. I would like to hear about it. All right, I haven't seen any questions come in. I'll just give it another moment here. If you guys are all set and nothing comes in, we'll jump off and call it a day. All right, I think that's it. David, do you have any last comments, or are you good?
No, that's all good.
All right. Thank you, everybody, for joining. Like normal, we'll post this on YouTube, and there's a direct link to a box folder there down below. And you can get our share files. You can get the slide deck to review later. So thanks a lot for attending, and keep an eye on the schedule for our next topic.
Thank you very much, everybody.
Thanks.